we are going to be going from this pile of parts to this, a fully functional 3D printed harmonic drive. With this one, has a 94, 95-ish to 1 gear ratio. So these are the parts that you need to assemble the harmonic drive. So you have the three 3D printed pieces. So this is the flex spline, this is the strain wave gear, and this is the circular spline. I already have the bearings pre-inserted, so in the strain wave gear I have a 608 bearing which goes in the middle there. You can just pop that in. And then on the circular spline there are two 6/8/14 bearings. They get press fit in on the top and bottom. They're a little bit hard to get in. I had to kind of stomp on the floor with them to get them to go in. But they do in fact go in even with no tolerances. So the first thing you're going to want to do is get your circular spline, and on here, I don't know if you can see, there are little dots. So there's one dot there, two dots there, and a line there, and those are all correspond to different tolerances depending on your printer. So on this current design, I'm going to use the one that has this line here. That's the tolerance which works best. So these are special wafer head nuts, or wafer head screws. They're M5 wafer heads. And then these are 625 ZZ bearings, just two of them kind of stacked up. So what you're going to want to do is put them like this. So your two bearings go on your screw. You have two of them like that. And then you have M5 nuts here. Those go in the bottom in these little captive nut screw holder things. So because I'm using the spacing with the line, I'm going to put the captive nuts in there, and then put the screw in the bottom, screw it in a little bit. Okay, now that both screws are kind of in place, you're going to want to tighten them down all the way. Because it's a wafer head, and I have modeled it so the strain wave gear acts kind of like a washer. You don't have to worry about over tightening them. They'll stay in place. So tighten them up. So you'll have it look like this on your strain wave gear. You have the bearing in the middle, and then the two double stacks of bearings on the side. And that's the strain wave gear done. So then you want to take your circular spline, and this flat face here, which the motor mounts to. The circular spline gets pressed in like that. The tolerances allow for a pretty tight fit, so it might be a little bit difficult to get it in place. But like that, as you see, it all fits in place. It's flush, and then the next thing you want to do is get your belt. So this is a 65 tooth custom shaped belt, which was printed in nylon from Shapeways. I highly recommend doing this. You might be able to print it on an FDM printer, but this is SLS in nylon, so it has really good mechanical properties, and it fits perfectly. So you're going to want to get your belt, and it's going to be a really tight fit, but you want to make sure that there's the same amount of space on either side, and then push it into place. And the belt fits in just like that. So if you spin it, you can see that the inner belt does make contact with the teeth, and then it's all working properly. Once you get that in place, you can take your flex spline. I already have brass inserts pre-inserted, so these brass inserts will just allow you to mount some sort of attachment or mount something to the output shaft. In this case, I'm going to be mounting this, but that'll come later. So what you're going to want to do is take your flex spline, kind of put it on the top, and just wiggle it around, and then it'll press fit into place. So technically, well, as you see, if you spin the input shaft, the output does turn, but nothing's being held together. So what you're going to want to do is take your M8 35mm hex bolt, put it in this hole here, as you see, it fits right in place, and it goes through that 608 bearing. And then take your M8 lock nut, thread that on, and your wrench, and tighten it into place. You don't have to go that tight on it. So you don't have to go that tight on the M8 bolt. See that here how it is kind of wobbly? You don't want that. You want to tighten it just enough so that there's no wobble in that M8 bolt. Like here, there's no wobble. So that's good. That's like the whole main assembly done. And as you can see, everything works and spins perfectly. So then the next step is mounting the motor to the main assembly that you just did. So in here, you can see that there's a little bit of play between the motor and the full assembly, and that just gives you enough distance to tension your belt. So you're going to want your M3 screws. Here I have them countersunk, but it really doesn't matter. The design is meant for countersunk screws, so I would recommend using those, but you might be able to get something else to fit. So put all of those in. So now that you have all of the M3 screws in, they're not super tight, so you can still kind of slide it around, and that'll allow you to tension the belt, which will go on later. So now you take your pulley gear. This one is a 40 tooth, but you can use probably up to an 80 tooth gear, all the way down to a 16 tooth gear, depending on the gear ratio that you want. So right now, the harmonic drive itself is set up for a 65:2 or 32.5:1 gear ratio. So you can change this pulley size out depending on what you want. So this outer ring is 116 teeth, and this one is 40 teeth. So that'll lead to a total reduction of about 94 to 95-ish to 1. So then put your pulley on. Put your belt around the pulley and the ring, and then you're going to want to tension. You're going to want to hold it so you can put tension going on the motor, a lot of tension, and then tighten the 4 M3 bolts. And now that the M3 screws are tightened, you can kind of visually just kind of line up like where you need this pulley to go. You want to make sure that you have the set screws facing the flat side of the motor there, but just kind of eyeball it so it's level. So once you've eyeballed the levelness, you can tighten all of the set screws on your pulley, and you are left with a fully assembled 3D printed harmonic drive. So as you see, all of the input turns really well, and if you look at the output, I turn the input gear and the outputs turns. Okay, now that we have the harmonic drive fully assembled, I am going to do some tests with it. So the first thing I'm going to do is set up an apparatus for a torque test. So how I'm going to do this is that I have these two pieces here, a 3030 aluminum extrusion and this plate, this like mounting bracket. I'm going to mount that to the 3030 extrusion and mount this to the harmonic drive, clamp everything down, and measure the torque and backlash that this thing has. Now that the harmonic drive is connected to the 3030 extrusion, we should be able to just clamp the harmonic drive down to a table, add a hook to the end of this, add some weight to the end of it, and see how much load we can add to get the torque. And with this, we can also get the backlash, just kind of by putting it down on the table and seeing how much it moves. Okay, so right now I have the harmonic drive hooked up properly, or clamped down. So I have 2 pieces of wood and a clamping it down to my work table. And then at the end, I have a force gauge hooked up, which will allow me to measure the amount of force. I've already weighed out this aluminum extrusion, and it is about 450 pounds, which is about 0.992 pounds. So, and the center of mass acts in the middle, and because the bar is 2 feet long, the torque just inherently in the bar is about 1 foot-pound of torque. So I've already done a few tests, like with just stationary torque and backlash, and I have a feeling that I may have broken a few teeth or broken some things inside the harmonic drive because it made some clunky noises. And now there's a bunch of slop. So if we go to test the backlash of this, so this is it just stationary under its own weight, and if we push it up, that's about the amount of slop we're getting over a 600 millimeter length. And I measured that to be about 1 centimeter, at maximum 2 centimeters, depending on the drive position. But before, I was getting about that much slop. So I tend to believe that I broke something inside the actual drive itself. I don't know if you'll be able to see this. I'll zoom in on the drive gears itself. So when I actually lift the thing, you see how the input gears are moving and the belt gears are moving. So it's attempting to backdrive itself, even though it shouldn't be able to. So I feel that A, either something broke, or B, the bearing positionings. So these bearings here, they're out of alignment now because of the torque that was going through it. So, as you can see, everything's all hooked up, ready to go. I have it hooked up to a Duet Wi-Fi, and I have RepRap firmware running that I'll be able to send codes to manually to show the movement of the arm. So the first thing I'm going to do is send a few codes just to make the arm move itself. So, as I said before, I did the torque tests and tolerance tests already, and think that I broke something on the, in the drive itself. So these tests aren't like the maximal tests that this drive is capable of. When I was testing before and pulling this down just without load, I got up to 10 pounds of force at 2 feet, so that is about 20 foot-pounds of torque. I don't know what that is in Newton meters. I'll probably put it up on the screen. But now with the tests, after doing that, you can kind of, this is the noise it makes. It doesn't make a very good noise. I believe that is the belt slipping or something cracking. As you can hear, the drive makes some cracking noises now. So I think something's broken on the inside. But doing that, you get about 5 foot-pounds of torque, or 5 pounds of force over 2 feet, so that's about 10 foot-pounds, plus the 1 foot-pound that the bar is, so you're getting about 11 foot-pounds of torque right now with it broken. And then if I send a code, which just has the drive move, you'll see that it is a little bit wobbly, and I believe that is because something is broken on the inside. Before, it was not like that. So if I send it, you can see it looks kind of smooth, but sometimes it hits catching points, and I have a feeling that that is one of the ear teeth breaking on the inside of the drive. and it's just rotating around and hitting it. But then if I go back to our 0 angle, you'll see it again. It's fairly smooth, but sometimes it hits some catching points. That wasn't there before I ran the first set of torque tests, but it is now. And then if I run the test and put the weight, or put some weight on the arm, so it's moving upwards now, I hold this, you get about 3 pounds before the motor stalls out. But then the holding torque is about 5 pounds, which isn't too bad considering it's broken. I'm going to take it apart and see what's the matter with it, and then update on what broke and or is wrong. Okay, now that we have the harmonic drive and torque tests off of the clamping rig, I'm going to take everything apart on camera and see if anything is broken. And then if something's broken, I'll update you on what I think happened, and what I might be able to do to fix it. Okay, so I just took the torque piece off, and from the outside everything looks to be normal. As I start tearing in a little bit farther, I'll tell you if anything else is different. Okay, so I just got the first actual piece off, and from the looks of things, there doesn't seem to be any noticeable breakages or cracks in this. So this is the flex spline. Everything looks good. Okay, so now moving on to the belt. Mostly, some parts, it looks decent. But if you look closely, some parts, you'll see that they have deformed a little bit. I have a feeling that is because the load was too great and it slipped, and such high amount of forces caused it to kind of deform and melt, and that would explain the differences in backlash and tolerances depending on what position the belt is in. On the inside of the belt, I see that there's a little bit of wear, but that's expected due to bearings being ran on the inside, but overall it seems smooth. The only thing, as I said, I can see that's wrong with the belt is that there is some deformation right there on the belt, and then on that same place on the opposite side. So I have a feeling that the bearings were in this position when it slipped and just kind of misshaped this part of the nylon belt. Okay, I just took off the strain wave generator, and everything seems to be looking okay with this. There doesn't appear to be any flaw that I can see on the drive belt ring or on the bearings. The bearings look to be centered and in the same place, and they seem to be square, just how they were when I put them in. So I believe that this piece is fine and hasn't had anything happen to it. Looking at the circular spline, very similar to the belt, it's mostly fine, but in some places you can see some deformation, like right there. There is some deformation of the gearing on the inside, and then if I move over to the other side, it's almost exactly symmetric, so there's some wear right there too. And I believe that the belt, this little belt, these two were in contact right there when I first did the torque test, and the belt slipped, causing the deformation in this belt and the deformation on the circular spline, and that was also causing the increased amount of backlash. Okay, as for solutions on how to fix this flaw in the harmonic drive, I believe that I may need to run some sort of lubricant in the future, just to help with heat tolerances, and I may need to make the gears or the tooth profile of this a little bit deeper, so there's some more to for the belt to bite into. If you look at it, there are some deformations in the print itself, just because of the speeds that I was printing this at. The teeth aren't exactly symmetric, like some of them are shifted one way, some of them are shifted the other, and I feel that that may have had some sort of effect on the like strength of them and where they were slipping. And then looking at this, I think the same thing, maybe just printed a little bit slower, but overall this piece seemed to be very solid. This one, obviously, there isn't much I can do about this because of the slippage. I could possibly make the tooth profile bigger, as I said on this, just make the teeth bite in a little bit more, but that might not be possible due to the teeth having to fit in smoothly. And then with this piece, everything was fine. The only problem with this is a few like issues that I had while actually printing it. It's like slightly warped, but overall that didn't really have an effect on the drive itself. So in short, I am quite pleased with how the drive performed. It performed, I would say, admirably considering the conditions it was under, especially the ones that you guys saw the actual test for. The unrecorded tests went a lot better, and that was before the teeth started slipping. Because of the deformation on the belts and such, I was getting about 21 to 22 foot-pounds of sustained torque on this, and then like that static torque on this, and then under load I could achieve about 13 to 14 foot-pounds of like active torque. So now the next thing to do will be to order a few more of these belts. As I can see, these belts are going to be somewhat of a, especially under high torque conditions, these belts are going to be a consumable, so I don't think they'll last forever. And then another thing I may have to do is increase the actual height that the belts act, or the actual engagement of the belt. So right now there's a 6mm engagement, so as you can see the belt only goes in 6 of its 12mm. I may have to increase that to 10mm or something like that, just so the belts have a larger surface area to engage, which would increase the sustained or the maximal torque that it can withstand. So I hope you liked the video. Like it if you liked it. Comment on anything you liked about my design, anything you'd do differently. I take that feedback seriously. And change my designs based on it. I have the Thingiverse file, or the Thingiverse page, linked in the description. It contains the STL files that I used for the actual drive itself, so it's just the belts. I have a 65 tooth and a 63 tooth version, the flex spline, strain wave generator, and circular spline. Those are all available on Thingiverse, as well as the Fusion 360 file, which has all of the hardware and stuff implemented, so you can get your bill of materials from that if you want to make one, or modify it at all. Feel free to do that. I just think that this is a very modular design. It's very compact, and overall I feel that it has very many use cases in like the rep wrap and 3D printing as a whole. So if you liked the video, as I said before, make sure to comment, like, subscribe, do whatever you do, share it. it would be really cool if people gave their thoughts on it and possibly made revisions and made it even better than I did. So until next time.